Brownian motion or pedesis, from ancient Greek, pi delta eta sigma iota slash psis slash leaping, is the random motion of particles suspended in a fluid, a liquid or a gas, resulting from their collision with the fast-moving atoms or molecules in the gas or liquid. This transport phenomenon is named after the botanist Robert Brown. In 1827, while looking through a microscope at particles trapped in cavities inside pollen grains in water, he noted that the particles moved through the water, but he was not able to determine the mechanisms that caused this motion. Atoms and molecules had long been theorized as the constituents of matter, and Albert Einstein published a paper in 1905 that explained in precise detail how the motion that Brown had observed was a result of the pollen being moved by individual water molecules, making one of his first big contributions to science. This explanation of Brownian motion served as convincing evidence that atoms and molecules exist, and was further verified experimentally by Jean Perrin in 1908. Perrin was awarded the Nobel Prize in Physics in 1926 for his work on the discontinuous structure of matter. Einstein had received the award 5 years earlier for his services to theoretical physics with specific citation of different research. The direction of the force of atomic bombardment is constantly changing, and at different times the particle is hit more on one side than another, leading to the seemingly random nature of the motion. Brownian motion is among the simplest of the continuous time stochastic, or probabilistic, processes, and it is a limit of both simpler and more complicated stochastic processes. See random walk and Donsker's theorem. This universality is closely related to the universality of the normal distribution. In both cases, it is often mathematical convenience, rather than the accuracy of the models, that motivates their use. History. The Roman Lucretius's scientific poem on the nature of things, c. 60 BC, has a remarkable description of Brownian motion of dust particles in verses 113-140 from Book 2. He uses this as a proof of the existence of atoms. Observe what happens when sunbeams are admitted into a building and shed light on its shadowy places. You will see a multitude of tiny particles mingling in a multitude of ways. Their dancing is an actual indication of underlying movements of matter that are hidden from our sight. It originates with the atoms which move of themselves. Then those small compound bodies that are least removed from the impetus of the atoms are set in motion by the impact of their invisible blows and in turn cannon against slightly larger bodies. So the movement mounts up from the atoms and gradually emerges to the level of our senses, so that those bodies are in motion that we see in sunbeams, moved by blows that remain invisible. Although the mingling motion of dust particles is caused largely by air currents, the glittering, tumbling motion of small dust particles is, indeed, caused chiefly by true Brownian dynamics. While Jan Ingenhousz described the irregular motion of coal dust particles on the surface of alcohol in 1785, the discovery of this phenomenon is often credited to the botanist Robert Brown in 1827. Brown was studying pollen grains of the plant Clarkia pulchella suspended in water under a microscope when he observed minute particles, ejected by the pollen grains, executing a jittery motion. By repeating the experiment with particles of inorganic matter, he was able to rule out that the motion was life-related, although its origin was yet to be explained. The first person to describe the mathematics behind Brownian motion was Thorvald N. Thiele in a paper on the method of least squares published in 1880. This was followed independently by Louis Bachelier in 1900 in his PhD thesis The Theory of Speculation, in which he presented a stochastic analysis of the stock and option markets. The Brownian motion model of the stock market is often cited, but Benoit Mandelbrot rejected its applicability to stock price movements in part because these are discontinuous. Albert Einstein, in one of his 1905 papers, and Marian Smoluchowski, 1906, brought the solution of the problem to the attention of physicists, and presented it as a way to indirectly confirm the existence of atoms and molecules. Their equations describing Brownian motion were subsequently verified by the experimental work of Jean-Baptiste Perrin in 1908. Einstein's theory. There are two parts to Einstein's theory. The first part consists in the formulation of a diffusion equation for Brownian particles, in which the diffusion coefficient is related to the mean squared displacement of a Brownian particle, while the second part consists in relating the diffusion coefficient to measurable physical quantities. In this way Einstein was able to determine the size of atoms, and how many atoms there are in a mole, or the molecular weight in grams, of a gas. In accordance to Avogadro's law, this volume is the same for all ideal gases, which is 22.414 liters at standard temperature and pressure. The number of atoms contained in this volume is referred to as Avogadro's constant, and the determination of this number is tantamount to the knowledge of the mass of an atom, since the latter is obtained by dividing the mass of a mole of the gas by Avogadro's constant. The first part of Einstein's argument was to determine how far a Brownian particle travels in a given time interval. Classical mechanics is unable to determine this distance because of the enormous number of bombardments a Brownian particle will undergo, roughly of the order of 1014 collisions per second. Thus Einstein was led to consider the collective motion of Brownian particles. Physics. The diffusion equation yields an approximation of the time evolution of the probability density function associated to the position of the particle going under a Brownian movement under the physical definition. The approximation is valid on short time scales. The time evolution of the position of the Brownian particle itself is best described using Langevin equation, an equation which involves a random force field representing the effect of the thermal fluctuations of the solvent on the particle. The displacement of a particle undergoing Brownian motion is obtained by solving the diffusion equation under appropriate boundary conditions and finding the RMS of the solution. This shows that the displacement varies as the square root of the time, not linearly, which explains why previous experimental results concerning the velocity of Brownian particles gave nonsensical results. A linear time dependence was incorrectly assumed. At very short time scales, however, the motion of a particle is dominated by its inertia and its displacement will be linearly dependent on time, delta x equals v delta t. So the instantaneous velocity of the Brownian motion can be measured as v equals delta x slash delta t, when delta t tau, where tau is the momentum relaxation time. In 2010, the instantaneous velocity of a Brownian particle, a glass microsphere trapped in air with an optical tweezer, was measured successfully. The velocity data verified the Maxwell-Boltzmann velocity distribution, and the equipartition theorem for a Brownian particle. The Brownian motion can be modeled by a random walk. Random walks in porous media or fractals are anomalous. In the general case, Brownian motion is a non-Markov random process and described by stochastic integral equations. Levy characterization. The French mathematician Paul Levy proved the following theorem, which gives a necessary and sufficient condition for a continuous or n-valued stochastic process X to actually be n-dimensional Brownian motion. Hence, Levy's condition can actually be used as an alternative definition of Brownian motion.
Please subscribe and thanks for watching.